So I debated not even making this last video on trig powers, but I think I should just for sort of completion. And then we'll get into partial fraction decomposition, the other topic in this chapter. What I want to talk about in this video is in the previous two videos, we just talked about products of sines and cosines raised up to powers. Right? And if the power on the sines and cosines were even, we did one thing. And if the powers on the sines and cosines were odds, we did something else, informally speaking. And we liked the odd and we didn't like the even. You learned some techniques and you're good with that stuff now. It turns out that similar work can be done with secants and tangents. And the reason you can do the same thing with secants and tangents that you can do with sines and cosines is just how sines and cosines are related. Secants and tangents are related similarly. And what I'm getting at is the Pythagorean identity relates together sines and cosines, right? Sine squared plus cosine squared equals 1. But if you divide each of these three terms by cosine squared, and you know that sine over cosine is tangent and 1 over cosine is secant, you can come up with kind of an alternative form of the Pythagorean identity, which relates together secants and tangents. So just like you can relate together sines and cosines with the Pythagorean identity, you can also relate together secants and tangents. But wait, there's more. Just like the derivative of sine gives you cosine and the derivative of cosine gives you negative sine, just how the derivative of each of those guys kind of refers to the other guy, the same thing happens with tangents and secants. The derivative of tangent, as you may recall from like a Calc 1 class, is secant squared. And the derivative of secant is secant times tangents. So not only are the functions themselves related according to the Pythagorean identity, their derivatives are related as well. And those two facts allow us to do similar things to what we did above with sines and cosines with secants and tangents. And we're only going to look at two cases. These are the two most common cases. This first case is when you have an even power on your secant term. So in this case, it's a 4. And in this case, tangent ended up being even as well, but it doesn't matter. Tangent power can be anything you want. It's the secant power that matters. And when your secant power is even like it is here, what you can do is kind of the same trick we did with odd powers of sines and cosines. So maybe you have to think back. This was a couple videos ago. When we had odd powers of sines and cosines, we did the same trick every time. We'd peel off one of them. Right? If you had sine cubed, peel off one of those sines and mess with the rest of them. Right? Save that one sine for the du. If we had cosine to the 5th, peel off one of those. You're going to save that for the du later on. And then the rest of those cosines you can deal with according to the Pythagorean identity. There's the same idea in each of those problems. Same thing we're going to do down here, except instead of peeling off one of them, we're going to peel off two of them. So if I have secant to the 4th x, like I do here, I'm going to instead think about that as secant squared x times secant squared x times however many tangents that I have, in this case 6 of them. So instead of just peeling off one secant, I'm going to peel off 2 secants and save that for my derivative. Why? Because the derivative of tangent is secant squared. I'm going to need 2 of them for my du, informally speaking. But wait, if your du is going to be secant squared, that means your u's are going to be tangents, but you don't have just tangents here. You have these tangents, but you also have some secants. You can't have secants and tangents if you're going to let u be equal to tangent. Right, we have to change these secants into tangents. If only there was some relationship between tangents and secants. Oh, right, this thing. Right, I can change all of my remaining secants into tangents according to this identity. And that's why it was important there was an even power on secant of x, because I was going to take away 2 of them to save for the du, and that would leave me an even amount of them. And as long as I have an even amount of them left behind, I can use this identity, which relates together even powers of tangents and secants. If I rewrite this secant squared here as 1, or tangent squared plus 1, I'll write it in the same order as it appears up in your identity, and then I still have tangent to the 6th x. You can kind of see where this is going to go. I forgot my dx in the prior line. I'm going to let u be equal to tangent of x, so u squared plus 1, u to the 6th, that'll all be easy enough. We do this substitution right here, and what we're left with is u squared plus 1 times u to the 6th power du. And this is easy enough that maybe you'll let me get away with even cutting out some steps. U to the 6th, I'll distribute that through. So I'll have u to the 8th plus u to the 6th. And then the antiderivative of that u to the 8th will be 1/9 u to the 9th. But I don't want to write 1/9 u to the 9th because my u is tangent of x. So I'm going to write 1/9 tangent of x to the 9th power. Similarly, the u to the 6th times the 1 will give me u to the 6th. The antiderivative of u to the 6th will be 1/7 u to the 7th power, but I'm not going to write 1/7 u to the 7th power. I'm going to write 1/7 tangent of x to the 7th power because u is just tangent of x. And then I'll remember to tack on my plus c, and I'll call this example good. And so maybe you're like, okay, I guess that'll work fine as long as I have an even power on my secant, but what if I don't? Like down here where I have an odd power on my secant. Well, if you have an odd power on your secant, you can't do this little trick. but it's possible that there's a saving grace. If your tangent has an odd power, then there's still a way you can get them done. If this is odd and this is even, well, that's bad news, and I'm not going to show you a way to deal with that. But if this is odd, bad. But if this is odd, oh, don't worry, that'll save you. Example 2, you have an odd power on tangent. And oh, by the way, you need at least one secant to do this method. In this case, I have secant to the 5th power. What you do this time is kind of the opposite of what you do here. Instead of my u being equal to tangent, in which case my du is secant squared, my u is going to be equal to secant. Well, if my u is secant, then my du will be secant times tangent. So what I have to do is peel off one of these secants and one of these tangents, one of each of them, to save for my du. You can kind of see that here. Here's the secant and the tangent, and if I started out with 5 of these secants and peeled one off, I have 4 left. If I started out with 3 tangents and peeled one off, I have 2 left. Now you see why we needed at least one secant, because I needed a secant times a tangent here, and if I didn't have any secants, I wouldn't be able to come up with that. But as long as I have at least one secant and the power on my tangent is odd, then I can peel off a tangent and I'll be left with an even number of tangents. The number of secants that I have left, it doesn't matter at all. It could be odd, it could be even, it's not going to matter. And the reason why is because the secant is going to become the u. So it's the tangents that I have to change into secants, because I'm going to make the secants the u, so this secant times tangent is the du. So to change my tangents into secants, I go back to this identity, and I realize that in order to change tangents into secants, it's important that the exponent on my tangents is even, so that I can use this identity. This identity tells me that tangent squared x equals secant squared x minus 1 if I subtract 1 from both sides of this equation. So when I change this tangent squared into secant squared x minus 1, what I have is this line here. And it might not look really nice, this line, but this line is really close to done. This line is going to work out perfect for our substitution. Here's our du, and these are just going to be a bunch of u's. U to the 4th times u squared minus 1, that's going to be easy. I find it somewhat satisfying to do this u substitution because things just go away so nice. This, and this all just change into my du. Cool. Secant to the 4th, I can just change that to u to the 4th. Nice. And then secant squared minus 1, that's just u squared minus 1. So I end up just evaluating this integral, pretty similar to the integral I evaluated here, which maybe you're getting really good at these and you don't even need to write this out in 2 steps. You can be like the antiderivative of the u to the 6th that I would have if I distributed this through is going to be 1/7 u to the 7th, but I'm not going to write 1/7 u to the 7th. I'll instead write 1/7 secant of x to the 7th power. And similarly, the minus u to the 4th, the antiderivative would be 1/5 u to the 5th. But instead of writing u, I'll write secant. And then I'll tack on my plus c, and I'll call this good. So a couple of examples of how you can deal with secants and tangents given some criteria. Not super important to be an expert with this stuff, but I think you find one homework problem that's similar to one of these two, and now you have something that you can reference so you can do all the homework problems.